Hello, everyone. Welcome to our webinar, Building a Secure Energy Future, Dynamic Stability Studies. Our presenter today is Chris Nelson, and this is one of our 4 2023 webinar events from Commonwealth Associates. So thank you for joining us today. A couple things to know about today's presentation is that this is worth 1 PDH credit hour. So if you do need credit hours and you'd like to redeem this time as a credit, after the event, you will get an email from Commonwealth, and that email will include a certificate of completion of this webinar, plus some language in the email saying that this email, along with the certificate, is enough to suffice and stand in to represent that credit when you need to report on that. Then our next webinar is actually going to be December 12th. It's on substation physical security. So we are very excited to present that webinar to everyone, but then we're most excited about our presentation today. Our presenter here, Chris Nelson. Chris, could you introduce yourself?
Sure. My name is Chris Nelson. I've been working in the power industry for a little over a decade. I started out with relay settings. After that, we did a lot of different types of studies, and lately I've been focused a lot more on generator interconnection and dynamic stability studies.
Great. Well, I'm excited to hear what you have to say today, and so thank you for presenting, and I look forward to the rest of your presentation. All right, Chris, take it away.
All right, thank you. So this presentation is on dynamic stability, and in general, what dynamic stability is it looks at a very short time window. So maybe 30 seconds of response of what happens to the power grid after a fault or a disturbance. So it uses the steady state power flow for the start of its data, but it also needs some much more detailed data on how the generator responds to short time period stuff. It's also called transient stability, and there's a couple of other names for it. I will try to call it dynamic stability just to keep the confusion down. So some of the problems with running the dynamic stability is it just takes a lot of input data, and the output data is, it depends entirely on having good, clean input data. So if you don't have a good model from the utility, or if you are the utility and you don't have yourself a good model, it's not going to give you very good results. So the graph I showed on the previous screen, if you don't have a disturbance, if there's no fault on the system, most of these lines should just be straight lines. So that's what they call a flat start. So if basically everything is steady state if there's no disturbance. So some other hardware challenges for actually running the dynamic stability is that there's just a large amount of data plotted. So for 30 cycles you plot, there's going to be several data points for each cycle, and there's a lot of different data that needs to be saved between the voltage, frequency, megawatts, megabars, and a few other things. It's just a large amount of data output, and that's partially a problem for hard drives, but mostly it's a problem for just the computers crunching it. So every time you do that, you usually run several different faults too, so it's a lot of data to go through. So some of that is that it takes a large amount of simulation time to actually run it. For just a regular laptop, it could take half hour per run or several hours. Sometimes you just run it overnight. If you have a better computer or parallel computing set up or a good server, it can be a lot faster. Some of the other problems that go along with this is that a lot of these programs are generally a little bit older, and they're very GUI friendly. There's a lot of programming that goes into it. So usually Python for most of them, and you also have to know, you have to be able to read the graphs that output and know at a glance what they mean. So there's a lot of both technical and engineering understanding that have to go into it. And after you have the data, you have to review it. There can be thousands and thousands of graphs depending on the size of the project. And if you find an error in some of those graphs, it can either be an error in the actual system or an error in the Python code or an error in some of the data. And if you find an error, you might have to rerun the whole analysis and let it run again, which can take a couple hours or however long it took to run the first time. So there's a couple different ways that this can be studied. The utilities, it usually depends on the utility or the interconnection, the ISO above it. So sometimes they do a single system study that'll just be the generator, maybe a transformer and a couple of lines, basically hooking up the generator to the PCC or the point of common coupling, and that's all that's studied. So there would be a fault at the top of the system, and you'd look at how the generator, usually it'd be an inverter, but not always, how that responds to it. The other way to study it is to take that small system and actually hook it up to the full utility, and they would put a fault on either the POI or maybe several buses away, or sometimes more, if they know their system well, they'll maybe put a fault on vulnerable spots, and they'll see how both the new generation and the existing generation react together to that fault. And sometimes the utility wants to look at both of those just to make sure they get everything. So some of the reasons they run this is that if a generator falls out of sync or can't maintain voltage or can't help bring voltage back up, it can cause a problem with the overall system. So it takes, usually, unless it's a large generator, the rest of the system can fix it, but they don't want any generators fighting against the rest. So they want everything to be able to fix it if they can. So if it's really bad, the misbehaving generators can cause pockets of the grid to fall out of sync, and that becomes a real major problem. So the dynamic studies really try to identify the problem areas so that they can be dealt with and figure out what's causing it. So these studies are required by most, but not quite all utilities when you do a generator interconnection application. Some of the utilities would run it themselves. Some of them would require the generator interconnection client to run it. So just to connect in the territory, they usually require it. Some are more strict than others, and they all have their different ways of doing it, but it's generally useful to have it done on all of them. Some of the tools we use to do it, the main one I've worked with personally is PSSE, transient stability, and that uses a lot of Python code to string everything together, and there's basically no GUI for it. There is a GUI that can do it, but it's only for running like small numbers of faults. It can't do a full study very well, so you use Python code to run the study and to generate the graphs. TSAT is a little bit newer program, I think. It's a lot more GUI friendly. I don't have a lot of experience with it, but I know it works well, and some utilities prefer it. We're in MISO territory here. I think MISO actually has a model for both, and they accept both for clients interconnecting. There are other programs that do it, but them seem to be the two main ones lately. So there's two types of models for a specific generator. One of them would be a generic model of the generator, and these tend to be fairly accurate, but not 100% accurate. They also come with the software. The user models are modeled specific to one generator, and I think they're distributed as a DLL. These generally only work for one specific version of a program. So it might work for PSSE 33, but it won't work for PSSE 34. And it probably won't work for TSAT or any other program either. So because those are specific to the generator, they're a little bit more accurate, but they're generally a little bit harder to use. You find them a lot more in like odd types of generation that aren't mass market. Like the inverters will generally have a generic model because the solar models are pretty good. So when you see a plot, part of the analysis, when you have a fault or a disturbance, the plot will usually spike or drop in response to that, depending on what you're plotting. The oscillation can happen for a short period of time, but you expect it to go back to normal pretty quickly. And certain utilities have numeric limits on what they accept, so it's more than just a feel of it should go back soon. They'll say it has to go back to 95% of nominal after a couple cycles or something like that. What these limits would be depend on the utility, but they make it a little easier to analyze when you have a definite yes or no, this is good. So some of the things we can do if there's a problem or a problem we find in transient stability, we can tune the case and try to clean up the actual input data a little bit, adjust the dispatch, adjust the import and export power. We can maybe play with the contingencies and make sure they're good. We can review the generator model to make sure it's behaving as expected. So if you find a problem with the larger utility model, you can roll it back to just the smaller model with only that generator to see if it's behaving there, because sometimes it might just interact poorly with other generators and it may not even be that generator's fault. So once you verify that the generation is actually what's causing the issue, or to do that, you can run faults with the base case and not faulted. That's another thing you can do to make sure it's good, make sure it's running flat. Sometimes there can be software version issues, so we could try this in a different version of the software or a different software. If we've decided that the problem is our generation we're trying to add to the grid, so there's some other things we can do. Usually these are actual grid-based things. So you can have a special protection scheme to make it do something. Like if there's a contingency, you'll make it behave a little differently when that contingency is active so that it doesn't cause a problem. Utilities don't always like that, but sometimes they accept the special protection schemes. If you find that a specific inverter or generator is causing a problem, you can maybe substitute it with a different one. You can adjust the ride-through settings and maybe some of the other settings in the actual generator model. There's load shedding schemes that can help sometimes, and sometimes it's just not possible to put a new generation in an area. Sometimes that's because there's just too many generators in an area, and having a couple more megawatts on the grid just makes it unstable. So sometimes that's a possibility and you just won't be able to add it. So I was going to go through an example of some dynamic studies. This is a very basic system I created. This was based on a real system with a few numbers changed and all the names are changed. So we have a low side generator connected. I think this was an inverter connected at 0.55 kV. We have a transformer stepping up to 34.5. And then there's another transformer stepping up to 161 kV. And the POI has two lines exiting going to two different directions. So the reason it's actually running 102% capacity right here is I think this was actually a smaller generator, but I raised the generator without raising the transformer sizes. So it's running a little hot right now. That doesn't really cause a problem with the stability, those that I've seen. So one of the graphs we look at is the voltage response to a fault. We generally want it to be flat before the fault. So I put a fault on the system at 1 second, and I believe it runs 6 cycles. It might be 4 cycles, and then the fault disappears and it goes back to normal. So because the fault is fairly close to the POI, actually I think the fault is on the POI, but it's not a real severe fault. There's some impedance on it. It only drops down to 0.8 voltage. It spikes back up as the generator tries to fix it, which we actually like to see because the generator should be trying to fix low voltage. And then it kind of gets its way back down to normal, and it settles out about where it started. The left graph is the actual generator. The right graph is the POI. So they both do the same thing. It's just a little bit more severe at the generator than it is at the POI. So the angle of the system, or the angle of the generator, we also look at that. So that will usually spike or drop a little bit at the fault, and it should go back up to the system angle. So in this case, I don't think I have it shown here. Yeah, I do. That's what this is. The left graph is the average angle of the system. So the average angle of the system actually changes when we put the fault on. So the average angle goes from about 34 degrees to about 37, 38 degrees. So it goes up a few degrees. So when we put the fault on, we expect the generator to go up a little bit too. So it spikes when we put the fault on, it drops as it tries to fix it, then it comes back up and it settles about a degree higher than it was at the start. It's not quite matching the average angle, but it probably is matching the average angle or the angle of the system at that location. So the frequency response of the fault, we generally expect to see it spike or drop a little bit, maybe oscillate, but it should settle back down to the system frequency of 60 hertz. And this is typically modeled relative to the swing bus. So 0 is actually 60 hertz. So it goes up just a little bit and then back down and it settles. The POI actually, because the fault is at the POI, it spikes a little bit more and it settles. I think it takes a little longer to settle here, but I think I graphed it longer and it did settle eventually. But 0.005 is actually a pretty small deviation. So the fact that it doesn't settle right away is not that big a deal. Actually, oh, there we go. The real and reactive power. We expect the real power to drop when it gets faulted, spike back up, and then kind of settle out. The reactive power, we generally expect a little bit smaller drop, but because the voltage dropped, we expect the inverter or the generator to put out more megavars trying to fix the voltage problem. So it spikes quite a bit, and then it settles down back to where it started. So the fact that it spiked quite a bit is actually a good thing. We want it to try to fix the voltage problems by putting more megavars in the system. So a couple final thoughts on this. There's a lot more renewable generation going in, and that generally means inverters. And they're generally smaller amounts. They're not like gigawatts in one generator. They're much smaller. So there's a lot more generators in general going in, and because of that, and because there's a little bit less spinning mass on the grid with the inverters versus the large generators, it can become a little bit more of a stability issue having just that much renewable generation on. And I don't expect this to get any better anytime soon. We're pushing harder and harder for more renewable generation. So I expect the dynamic studies to be more in demand in the future. They are already pretty going up in demand as the utilities have seen where things are going. But the software tools to study them are also getting better. I think TSAT is, from what I've seen, TSAT is much easier to use than some of the older software, and it's a brand new thing. So actually, it might not be that new. It might be a couple years old, but it's not a couple decades old anyways. There's also more demand from the regulatory agencies to make sure stability is good for new assets being installed. And I guess that's all I have.
Thank you, Chris, for sharing with us today. My camera is getting on here right now. I appreciate your time and sharing your expertise with us on this really great topic. For anyone who is interested, you can email me and I'll get you in touch with Chris if you have any questions or any follow-up comments. We will also be posting this to our GoToWebinar stage channel where you can watch it on demand. Also, in that response email that you'll get thanking you for watching, you will also get a link to a video with recording on demand as well. Remember to redeem your PDH credit hour for this presentation. Take your email that comes after the webinar, along with your certificate from GoToWebinar concerning this event, certificate of completion, and that should be enough to qualify as proof of your credit earned. Last but not least, Substation Physical Security webinar, December 12th, 2023. Make sure you mark your calendar, as that subject and topic are really important, and then with the date recently solidified, we know that registrations will go quickly. So that is all I have today. Chris, thank you very much again for presenting today, and to everyone else out there. Yeah, I hope you have a really great day. Thank you very much.
Yeah, thank you.